So on your quiz, when we completed, what was it, number 3? Number 3, we went through everything. We found the critical points. We found increasing, decreasing. We found maximums. We found concavity. We found inflection points. Okay? That is what we're doing today, but we're going to take all of that information and we're going to create a graph out of it. Okay? Without our calculators, we can know everything there is to know about a graph. Okay? Now, this is going to require us to pull some information from pre-calculus. This is also going to ask us to pull some information from Unit 1 with limits because we need to know some end behavior. But a majority of it is what we did on that quiz the past 2 days. So, here are the steps I need you to take, or the things I need you to consider when you're going to graph a function. Okay. Now, these first 4 things deal with previous material, domain, that's pre-calc stuff, okay? Hopefully, we can talk through that. That will be one of the least of our worries, okay? And discontinuities, if we have a rational function, we need to identify our asymptotes or any holes if we have them. End behavior, if we have a polynomial, are we rising or falling to the right and left? If we have an asymptote, like a horizontal asymptote, this is where we would consider that. Intercepts are always helpful. Okay? If we can find them without our calculator, then those are easy points to plot. And then we can go through our first derivative and second derivative for them to help us with the information that we found on our quiz. I have 3 problems, but my guess is we will probably get through 2. We will go very slow through these, but these are going to take a chunk of time. Okay, you don't have very many in your homework assignment. And on your worksheet, there's only 4. Your homework assignment. You have 5 in your homework assignment, okay? And then you have 4 on your worksheet. It is kind of nice that you have the weekend to do the homework assignments since there is 5. But we're going to go through a polynomial one. It should be like jumping for joy if you see a polynomial one, right? But we're going to go through a rational one, and then if we have time, we'll go through one that has the corner. Okay? So this is our first one. F of x equals x cubed minus 3x squared minus 1. Back in pre-calculus, you did a polynomials chapter last year, chapter 2, and we went through all of the finding zeros and end behavior and all of that stuff, but I said, you know, we're not going to know where those terms are, so just, you know, make a rough sketch. Well, here's the time we actually get to figure out where all those terms are, okay? So the first thing we need to consider is the domain. We have a polynomial, so everybody, what is the domain? All real numbers. Okay. Since we have a polynomial, do we have any discontinuities? Which makes this sense, right? So let's talk about our end behavior. We need to consider the limits as x goes to infinity, so that means as we look to the right, And we need to consider the limit as x goes to negative infinity, so as we go to the left. Okay? So I'm going to give you 20 seconds to talk to your pod about what's happening to the right and left-hand side of this polynomial. 1, 2, 3, go. Okay, on the right side.
Up.
On the right side, we're going up. And on the left side, we are going down. Okay. Positive leading coefficient means we're going to rise. Rise to the right, excuse me. Odd degree means we're going to have opposite behavior. Okay. Intercepts, sometimes we're going to be okay finding these, sometimes they're not going to be feasible. Okay, y-intercept, that should always be okay. When we plug in 0 for x, what do we get? So we know we have an intercept of 0, -1. Now, if we put a 0 in for y and we try to solve that out, that's not a good one, right? If we can factor it, let's do it, but I'm not going to make you do the leading coefficient test to find these zeros. Okay, it'll be okay. I want to focus on the calculus. So, here's where we get to do some calculus. First derivative. Our first derivative. Caroline, what is it?
3x squared minus.
Awesome. Okay. So we can identify some critical points. Let's see, we want to factor out a 3x. Left over is x minus 2. So we have critical points of 0 and 2. Okay. Here's where it becomes very important that you label your number line. Okay. It wasn't a huge deal before, but now it's really important because we're using this information to graph. So if we put 0 and 2 on our number line, and remember we're plugging these intervals into the derivative to see if the derivative is positive or negative. Okay. Eli, what would be true about our derivative to the left of 0? Positive. Between 0 and 2, actually, what would be true? Negative. And after 2, Michaela, what happens? Or positive. Okay? So we can look, we know what this means, right? We know that our function is increasing, decreasing, increasing, which also should match this end behavior right here, right? Okay? But specifically, let's talk about what's happening at 0 and 2. What's happening at x is 0?
Maximum.
We have a maximum. So let's go ahead and label that. We have a maximum at x is 0, and we already know that when we plug in 0, we have -1. So our y-intercept is also a relative maximum. What's happening at 2? We have a minimum. Okay? And if we go way back up to the beginning and we plug in 2 to x cubed minus 3x squared minus 1, what would that y value be? -5. Okay, so we have 2 coordinates to plot. That's good. Okay. Now let's find our second derivative. Okay. Here especially, as we go through different problems, you need to be a little bit strategic about which first derivative you use to take your second derivative, we can either do the product rule or we can do the power rule. What are we going to do? The power rule. In this problem, it is going to be to our benefit to go way back up here to this first derivative and take the second derivative. 6x minus 6. There could be times where you need the simplified version. Okay. So we said this equal to 0. What's our possible point of inflection? 1. I am going to label this as f double prime. To the left of 1, the value of our second derivative would be what, Brett? It would be negative. And to the right of 1, the value of our second derivative would be what, CJ? Positive. Okay? What does this tell us? This tells us that our function is concave down until 1, and then after 1, we are concave up. Okay, so kind of think about what that would look like. Since we have a change in sign right here, what is happening at x is 1? Okay, we have a point of inflection at x equals 1. Now, it is important that we know the coordinates so we can plot it. So we have to go way back up to the beginning. X cubed minus 3x squared minus 1. If x is 1, what is our y value? Okay. I'm going to try something. It may not work, but we're going to try it. I got to remember how to do it here. Okay, so now we're going to graph it. I know you have all of this written. I know it's kind of small, but you have it written down on your paper, right? Can you kind of see it okay? Yeah. Okay. Now you will have graph paper, like you'll have a graph grid that I will give you on your worksheet or on your quiz or on your test, all of those things. Okay? So I would plot all of the points that we found. Okay? We have a y-intercept of 0, negative 1. We also know that that is a maximum. So you know what I'm going to do? I'm going to write maximum. We have a minimum at 2, negative 5. And I'm going to label that minimum. And we have a point of inflection at 1, negative 3. So now we get to put it all together. Now, we're pretty familiar with polynomials. Some of us can imagine what this is going to look like. Okay. We know that we have to go from increasing to the max, decreasing to the min, and increasing after the min. Okay. While still keeping the concavity intact. We need to be concave down to the point of inflection and then concave up. Okay. And since it's polynomial, it needs to be nice and smooth. We have used calculus to make that graph as accurate as we can. Okay. Now, unfortunately, we have two imaginary zeros and one irrational zero. So finding a zero is just not going to be something we're going to mess with. But if we could find them, we will. that one was not very intensive as far as the derivatives and the algebra is concerned. So let's practice one to where we have a little bit more to worry about. Okay, that was a nice warm up, right? We're feeling okay about things. Now, you liked that one? Okay. Yeah.
Oh, it's just.
It's gonna be exciting, right, Trevor?
I don't know.
If I wasn't excited, there would be a problem.
Well, usually when you're excited, it's a tough one. So.
It's not tough. We just have a lot to keep track of as far as our algebra is concerned, right?
Think of it more as a challenge.
Okay, because when we take the derivative, what are we going to have to use?
Quotient.
Use the quotient rule, okay? That's why this one is just, it's going to be a little bit more intense, okay? Let's talk about our domain. Okay, since we have a rational function, we need to look at the denominator. And where is our denominator 0?
Negative.
Okay, so our domain is everything except -2 and 2. Now, without actually factoring this out, we can tell, are we going to have a whole, or are we going to have asymptotes? Or are we going to have both? We're just going to have asymptotes, right? We can see without actually writing it down that the numerator is not going to factor out, we cancel anything with our denominator. Okay? So, when we talk about discontinuities, we have asymptotes at x equals 2 and x equals -2. Okay. Now, if we have a horizontal asymptote, that's what I want you to consider with the end behavior. Do we have a horizontal asymptote? Okay, where did it go? Okay. Since the degrees are the same, we look at the coefficients. Okay. Our asymptote, horizontal asymptote, would be at y equals 2. A lot of 2's in this one, huh? So when we talk about end behavior, we know that our end behavior will approach our horizontal asymptote, which is 2. So I'm going to make a note to myself. Our end behavior is the way that it is because of our horizontal asymptote. Last pre-calc concept, excuse me. Our intercepts. Let's start with the easy one. When we plug 0 in for x, we're left with
9 over 10.
9 over 10. Okay. Now we need to plug 0 in for y. Now, if we're looking at where a fraction equals 0, we're really concerned about the numerator. So if we set this equal to 0, okay, we're talking about x is 3 and x is -3. Okay, ready?
Yes, ma'am.
This is where it gets fun. Buckle up. Thank you, CJ. Now I'll use some different colors here. We'll do everything for the first derivative in red. So our first derivative. Okay. So we have the derivative of the numerator times our denominator minus our numerator times the derivative of our denominator all over denominator squared. Okay, now before in unit 2 we got to leave it like this, but we need critical points, so we do need to go ahead and multiply things out and simplify. So if we were to distribute everything in our numerator, we would get 4x cubed minus 4x squared, please be careful here, minus 4x squared plus
It's 16. 4x times negative 4 in the first part.
So do you remember when I said be careful?
Yeah.
Be careful. So then we have negative 4x cubed and this becomes a plus 36x. Why is it a plus 36x?
Two negatives make a positive.
Because we have this negative here. This negative is easy to forget about when we're distributing over here. All right, so our first derivative. What does our numerator combine to be? 20x. That's nice. So we're going to look at our critical points, and here's where we have to remember that critical points occur both when our derivative is 0 and or undefined. So where is our derivative 0?
0.
0. Where is our derivative undefined?
Negative 2 and 2.
Okay, so our derivative is 0 where the numerator is 0. 20x equals 0 at 0. And then our derivative is undefined where the denominator is 0. So 2 and negative 2. Okay, I'll let you go ahead and fill in this chart for me if you would. Here is one where we really can't predict the pattern. Right? All right, so what are our signs? This interval. This interval. This interval.
Positive.
Ah, okay. Now, sometimes it doesn't work out like this, right? I would for sure, like, why are 2 and negative 2 critical points? What's happening at 2 and negative 2? Those are our asymptotes. So they're going to be critical points all the time because the derivative is undefined there, no matter what. So I would label these as asymptotes on your number line so you don't accidentally identify them as a max or min. Now, in this case, you wouldn't because the signs don't change, but they could. So I would label them so you don't try to identify them as something, okay? So really we need to look at 0. What's happening at 0? We have a minimum. So we have a minimum at x equals 0, and we already decided that that coordinate is 0, 9/2. Okay? So we are decreasing, decreasing, increasing, increasing. Now that sounds kind of funny, but remember we have asymptotes breaking those up. And so going from a decreasing to another decreasing interval, it will make sense when we go ahead and put it all together. Okay? All right. First derivative was not bad. Second derivative is where this is going to get a little intense. I'm not saying it's bad. I'm just saying it's going to be a little bit more algebra than the first time around. So we just need to be careful. All right, I'll switch back to blue here. Our second derivative. Okay, so we're going to use this one right here, right? Okay, so quotient rule, again, derivative of the numerator times the denominator minus the numerator times the derivative of our denominator. We're going to have to do the chain rule. So 2 times x squared minus 4 to the first times 2x. All over our denominator squared. Squared. Yeah, I said squared, and I meant to write 4. Thank you, Joe. Okay, so let's be a little strategic about this, okay? Okay, and that's exactly where we're going, okay? Do you see how there's an x squared minus 4 in both chunks in our numerator? Okay, and what's in our denominator?
X squared.
X squared minus 4, a lot of them, right? So what we can do, and what I'm going to go ahead and do, I'm going to make this a little easier on us. I'm going to write this as 20 times x squared minus 4 squared minus 20x times 2 times 2x would be
80x squared.
80x squared times x squared minus 4. I want this to be a little more visual for us, okay? So what we can do, and this is going to happen every time that you take a second derivative of a rational function, is you're going to be able to factor out at least one, if not more, of whatever that denominator was. So we can factor out an x squared minus 4. Left over would be 20 times the second x squared minus 4 minus, here left over would be an 80x squared. Okay, so this is nice, right? We get rid of some terms here. This x squared minus 4 can cancel out with one of those x squared minus 4s. And so now our numerator does not have as many terms in it. So what we're left with is x squared minus 4 cubed in the denominator. And our numerator, this is 20x squared minus 80x squared. And then we have 20 times negative 4. Yeah. All right. Yes, I understand that that was some intense algebra, but you all are fully capable of doing that, start to finish. You are. Okay? Just know that that'll be kind of a pattern when you do these. Okay. All right, so we need our potential inflection point. We need to know where our derivative is 0 and undefined. Now, if we set our second derivative equal to 0, we get negative 60x squared minus 80 equals 0. We get x squared is negative 80 divided by 60. I'm not even going to reduce that. Can that happen? Can x squared equal negative 80 over 60 in real numbers? No. Our second derivative is not ever 0. Okay? But we do need to keep in mind that it is undefined at 2 and negative 2. So let's talk about the concavity here before and after negative 2 and positive 2. Okay? If we were to throw a number less than negative 2 into the second derivative, what kind of value would we have? Negative. Okay, between negative 2 and 2, pick 0. What kind of number would we have? Positive. We would have negative 80 over negative 4 cubed. That would be a positive number. And then after 2, we would be back to negative. Okay? Now, same thing here. You want to go ahead and label your asymptotes so you don't accidentally identify them as a point of inflection. There is not a point of inflection at negative 2 and 2 because those are asymptotes. Yes, there is a change in concavity, which happens or could happen in between an asymptote, but it's not a point of inflection. Okay, so there are no points of inflection. All right, here it is, ladies and gentlemen. We're going to make this graph. And we're going to make it way more accurate than we've ever been able to. Okay, so let's see how, okay, so we're going to have to scroll a little bit, but that's okay. All right, so let's start with the pre-calc stuff. We have asymptotes at x equals 2 and x equals negative 2. And we have a horizontal asymptote at y equals 2. Our intercepts are helpful here. We have an intercept at 0, 9/2, 3, 0, and negative 3, 0. We can label that 0, 9/2. We know that that's a minimum. And we don't have any other relative extremes. Yeah, that's kind of what it's going to look like. Okay, so let's start to the left of negative 2. To the left of negative 2, our derivative is negative and our second derivative is negative. What does that mean? We are decreasing and concave down. We also know that our curve has to approach the asymptotes. So if we want to be decreasing and concave down, the only way to make that work is to make our curve look like that. To the right of positive 2, we are increasing and concave down. We also know we have to approach the asymptotes, so increasing and concave down going through that intercept looks like that. And then in between negative 2 and 2, we go from decreasing to increasing with that relative minimum, but we're always concave up with a positive second derivative. So like Joe said, it's going to have kind of that U shape. And that is a graph that you made last year in pre-calculus, so it's not like surprising. Okay. I will tell you that if you have a quotient, like a rational function as your original function, you're going to have some more intense algebra than the other ones. If it's polynomial, you won't have a lot of algebra. These require a little bit more algebra, so just be mentally prepared for that. You can do it, and you're going to tell yourself that you can do it, but it's just going to take a little bit more time and patience. Okay. Most important, your work has to match your graph. Okay? Some of you know what these graphs are going to look like, or roughly what they're going to look like without the calculus. Okay? The calculus gives us like exact information on where we have those points of inflection and those minimums and maximums. But some of you had an idea of, what this could look like. If your calculus does not match your graph, you will get docked points on the quiz and test. Okay? Whatever you have for your calculus, you need to make it match your graph. Okay? So if you think your calculus is wrong, you got to go back and fix it. But whatever you have for increasing, decreasing, concave up, concave down, min, max, that's got to be on your graph.
If our calculus does end up being wrong, will you grade the graph according to what we had?
Yes, I will. I will. Now, when you do these 5 problems this weekend, I do expect you to do them without a calculator. But if you use your calculator to check your graph, I have no problem with that. Okay? There are a few different kinds of problems that you will see, and we're going to practice those few different kinds of problems both this weekend and Monday. Okay? So some of this is getting used to the process. Some of it is getting used to these graphs that we've never been able to look at in pre-calculus because it really only makes sense with the calculus that we do. Okay? Now, if you have a derivative that is undefined, but there is not an asymptote there, what is your other option? What do you think? A corner, okay? There could be a hole, and you would identify that in the beginning, correct? But if there's not a hole or an asymptote, we could have a corner, okay? And that's going to happen in your homework, I believe. Okay. I have given you 3 odds and 2 even. So for sure 21, 23, and 15, you're going to be able to look at Calc Chat to help you with some work if you can't find a mistake. But number 6 and 8, they're even, and so you can at least look at your graphing calculator to check your graph. But the work in between, Calc Chat would not be helpful there. Okay, so does everybody understand that you're doing the book assignment that is labeled for yesterday? Okay. On Monday, we will discuss the book assignment, and I'll also, we'll get to go through some of the calculus from it if we need to, and then